Hi. Now we're going to start the new subject in our class, and this subject is, as I mentioned before, matrix algebra. Okay, let's start with the definition. Matrix algebra is a branch of mathematics that deals with the theory of systems of linear equations, matrices, vector spaces, and linear mappings between such spaces. Now, look, we of course are only gonna scratch the surface of matrix algebra, and we are gonna take out of it the most useful tools that we can use later on in economics, in finance, in management, in statistics. So the most important thing for us will be, of course, dealing with systems of simultaneous equations. But we will be also discussing matrices, because we need matrices and vectors, which are special cases of matrices, and vector spaces a little bit. And we will be using them to deal with the systems of simultaneous equations. Okay, so look, our goal in this class is to devise a method that, for example, look, this is a system of simultaneous equations that you probably seen in high school in some versions many times. Right? Look, this is a system of linear equations. By linear, we mean that, look, all we've got here are our variables, x's, x1, x2, x3, in the first power. So they are not in any other power, they are not multiplied by other variables, there's no complicated expressions over here. And look, our task is to devise a method that will allow us to solve any system of simultaneous equations like that. Okay, so how will we do it? We will first take a system like that and we will write it into so-called matrix form. And this form always looks more or less the same. So first, we will have a vector of coefficients. Look, in order to fill it, all we've got to do is to rewrite all the coefficients on all the variables. So we've got 7, -1, 10, -2, 1. Then we've got 6, 3, -2. Then we need to organize our variables over here, x1, x2, and x3. And then, of course, we have a vector of constants over here. Of course, I will explain all of this. I just want to show you more or less where we're going. Okay, but now you can say that, okay, but if it's useful to just linear equations, maybe it is not such a useful tool after all. Well, as it turns out, very often we can linearize equations. Okay, again, let me give you an example like this. Let's just say the system of equations you need to solve has the form a1 x b1 y equals a2 to the power b2. Well, it doesn't look like anything that we could solve as easily as before, unless we use some properties of logarithms that we learned about a couple of videos ago. Look, I can logarithmize this expression to get ln y equals to ln a1 plus b1 ln x. Then here I will have ln y equals ln a2 plus b2 ln x, because we remember that when I logarithmize things, logarithmize of a product is a sum of logarithms, and we can always take the exponent in front of the logarithm. And now look, if I would move parts with x over here, so I would have ln y minus b1 ln x equals to ln a 1, and ln y minus b2 ln x equals to ln a1, we are still able to use the same tools. Because look, now I can simply say that, let's just say that ln y is some z1, ln x is some z2. And now, look, I can put this system of simultaneous equations in a matrix notation. We have 1, 1, minus b1, minus b2. Here we would have z1, z2. And here we would have two constant numbers. Of course, here it should be 2, ln a1, ln a2. So, everything that we learn about matrix in matrix algebra for systems of linear equations, we can also apply very often into situations where we do not have a linear equation. Okay, but look, those are just examples, right? We don't want to know how to do case 3 by 3 or 2 by 2, because those are the cases we can use traditional methods. We are interested in more general tasks. This more general task is to solve system of n simultaneous equations with n variables. So our system would look like this: a1 times x1, a11 times x1 plus a12 x2 plus, until we would go to a1n xn, and this is equal to some d1. Then the second equation would be a21 x1 plus a22 x2 plus until a2n xn. And look, we would have a lot of equations like that until we would go to the final equation, equation n, which would have start with n1 x1 plus an2 x2 plus an xn. This is equal to d1, and this is equal to d2, and this is equal to dn. Okay. Of course, in order to solve system of n equations with n variables, we need to have at least n equations. We can have more, but if we have more, it means that usually the ones that we've got the ones we've got is too many. We don't need to use them all. But about this a little bit later. And now, what can I do with this? How can I rewrite this into matrix form? Look, again, we will start with this big table over here, and I will start a11, a12 until a1n. Here I will start with a21 and a22 until a2n. And we will go like this until we will arrive at a1, a2, until a-n. Then, over here, we will have a vector with all the variables, look, I hope you can see how we did it. Now, what do we have inside? Look, we have here all the coefficients from all the equations. This is why we call this matrix of coefficients. Then, next to it, we have all the variables. And look, normally we would just call it vector of variables, but we will be using this in different economic problems. So let's right away give the full name that we need. This is going to be a vector of endogenous variables. What does it mean endogenous? It means that they are explained within the model, but we will actually have a subject in which we will explain this in detail. Finally, this last column you can see over there is called either vector of constant terms, but for our purposes we're going to call it vector of exogenous terms. But of course, vector of constant is still an appropriate name. Okay, so now we said quite a lot about matrices and vectors. So what is a matrix? Well, let's use a very simple definition. And we're going to define matrix as rectangular array of numbers, coefficients, or parameters or variables. Now, what does the definition imply? Well, rectangular means that we will get some rectangular shapes. Because all the matrices can be written down in 2 dimensions, even when we are dealing with n-dimensional problems. Now, array means order. This actually is the key to understanding matrices. Basically, each element within a matrix has a specific location, and because everything is set up in a certain way, we can do operations about which we will be learning even today, and it will allow us to use a lot of properties of matrices. And of course, matrices can be filled with numbers, parameters, or variables. But I think this part is self-explanatory. Okay, so let's just say, let's discuss, so what's now that we know that basically matrix is a table with numbers or variables or parameters, and each of these parameters, numbers or variables need to be located in a specific order. So how do we construct those matrices? How elements are located? Look, so let's start with dimensions of the matrix. Okay, so if we have some matrix A, we are saying that this matrix A has dimension m by n. And look, m is number of rows. So, some matrix like this, then this matrix has 1, 2, 3 m rows. Rows are going like this. Remember, this is very, very important. Now, and we denote each row with letter lowercase I. Now, on the top, over here, we have columns, and n denotes number of columns. And we got them all here. 1, 2, 3, until n. Those numbers, of course, can be different. Of course, when we talk about system of simultaneous equations, matrix of coefficients is n by n. So it's a square matrix. Square because number of columns and number of rows are the same. But of course, it's not a rule. And of course, the columns in a matrix are going like this. And number of columns we denote by lowercase j. So look, in other words, we can say that matrix A is a collection of elements A, I, J, where I and J denote row, J column in which this element lies, for I equal to 1, 2, until m, and J equal to 1, 2, until n. Okay, and remember that we read this, what you see over here, as m by n. Okay, now, so this is the basic information. Based on A and I, you can locate a given element in a matrix. Okay, but we already said that there are some special cases of matrices. And those special cases of matrices are called vectors. So, vectors, look, vectors, unlike matrices, well, are, look, because matrices we will be denoting with capital letters, A, B, and so forth. Vectors, on the other hand, we will be denoting by lowercase letters, like X, V, U. Now, what is a vector? Vector is a type of matrix in which one of the dimensions, so either number of columns or number of rows, is equal to 1. So, for example, vector X is of the dimension, let's just say, n by 1, with elements x1, x2, until xn. This thing that you see over here, we will call column vector. Then, we can also, if we can have a column vector, then of course we can have just as well a row vector. We will be denoting row vectors as x prime for a reason. What is this prime? I will explain to you very soon. So this time we will have a vector 1 by, let's just say, okay, still let's keep it n, and it will look like this, x1, x2, until xn. Okay, so this is, I think, this is enough for us. This is enough information to for us to be able to actually start learning different operations on matrices, and this is what we're gonna do. This is what we're gonna do next. Okay, so now let's move to the topic of matrix operations. Okay, and we're going to start with equality, because look, so we're going to start with equality. So, basically, we say that two matrices are equal, so we can write that A is equal to B. Okay, and I'm going to use the symbol if and only if. Okay, maybe I'm going to just write this. If and only if and only if they have the same dimensions and identical elements at corresponding locations. Okay, so here we have two conditions. Basically, the first condition is that they must have the same dimension. So look, if I have matrix A that is 3 by 3 and matrix B that is 2 by 2, then I don't even need to look at anything else. They are definitely different because they just have different dimensions. Now, if we have two matrices with the same dimensions, okay, like for example, 4, 0, 3, 2, 0, doesn't work. Then this matrix is equal only to this matrix, and is different than if, for example, I would have 2, 0, 4, 3, or if I would just change one number, two numbers, 3, 4, 2, 0. Look, any change in the location of any element, so any difference, visible difference, creates a new matrix that is different from the previous one. Okay, so this is the most basic thing about operation on matrices. But look, when we had regular algebra and we were talking about numbers, now if I want to add 3 to 7, I can always do it, right? Doesn't matter what. I can always divide, I can always subtract number from a number, multiply, I can always divide, except for dividing by 0. So actually, before doing some operations, I don't need to think about whether I can actually make it happen. Now, the same is not true in case of matrix algebra. In matrix algebra, we need to have fulfilled so-called conformability conditions. So conformability conditions are conditions needed to be required if we want to perform some specific operation on matrices. And look, different operations will have different conformability conditions. Okay, so let's start with addition and subtraction of matrices. Okay, so what are the conformability conditions in case of matrix addition and subtraction? Okay, let's say that conformability conditions we will be denoting as CC. So CC, conformability conditions, in case of addition and subtraction for matrices are very simple. Matrices must have the same dimensions. So if I have matrix A and I want either to add or subtract it from matrix B, I need to make sure that if matrix A is m by n, then matrix B is also n by n. Because if either one, if we would have here, for example, we would want to add or subtract matrix C with dimension m by n minus 1, I already cannot do it. Both dimensions must be the same. And look, when I'll show you how to add and subtract matrices, I think this requirement will become pretty much self-explanatory. What do I mean by that? Okay, look, addition of matrices go like this. If I have a matrix A, so I have matrix A with elements A, I, J. I have matrix B with elements B, I, J. Addition of these matrices, or subtraction, it works the same, works like this, that I take all elements of A, I, J, I either add or subtract all elements B, I, J, and I get a new matrix with elements C, I, J, where each element of C, I, J is equal to A, I, J plus minus B, I, J. So look, I just in relatively smart way said very simple thing. If I have two matrices and I want to add them or subtract one from the other, all I need to do is to perform this operation on every element, on each corresponding element. So we add or subtract all appropriate elements. Okay, now the question is, so what else? I'm sorry. What else should we do over here? Okay, let's now maybe do an example. Okay, this is pretty much extremely easy. So let's do not concern ourselves too much. Okay, so if I have matrix 4, 2, 9, 1 and matrix 2, 0, 0, 7. Okay, so look, all I need to do is in line with what we already said, and I just need to add all corresponding elements. So 4 will be added to 2, right? I'll get 6. 9 will be added to 0. I will get 9. 2 will be added to 0. I will get 2. 1 will be added to 7. I will get 8. And what if we would now like to subtract those matrices from one another? And we proceed in exactly the same way. 4 minus 2 is 2. 9 minus 0 is 9. 2 minus 0 is 2. And 1 minus 7 is negative 6. And look, there's no more philosophy to it. So how about now we will move to another operation, which is multiplication by scalar. Okay, first, what is a scalar? Have we ever heard this term? Well, look, scalar is what we call a number in matrix algebra. Why do we call it like that? I will explain it later when we will be discussing some properties of vectors. Now, let's move on to multiplication by scalar. So look, now our task is simply to multiply some matrix A with elements A, I, J by some scalar K. Remember, scalar is just a number. How do we do it? Simply K times A is equal to K, A, I, J. Actually, you know what? Maybe let's explain why is it called scalar even now. Okay, imagine that matrix A is given by numbers 1, 2, 2, 4. Okay? And our scalar K is 3. So, if I want to obtain K, A, all I need to do is to multiply each element inside this matrix by 3. So what am I getting is now I get 3, 6, 6, and 12. Okay. Look what happened. Each element inside of this matrix is 3 times bigger. So can we say we scaled it up? Definitely. What if K would be equal to 0.5? Then AK, KA, okay, about this a little bit later, but KA would be 1 over 2, 1, 2, 2, 4, which is equal to 1 over 2, 1, 1, 2. What has happened over here? Now, each element in this matrix is twice as small, right? Can we say we scaled it down? Yeah, of course. So look, what a scalar does to a matrix and a vector. With vector, it's very nice to see on the graph. This is why we're going to do it. But you can see it also in the matrix. We can either scale everything up or scale everything down. And very important thing, it doesn't really matter. Actually, again, this is something we will be discussing in the future, but it doesn't really matter from which side you are multiplying a matrix by a scalar. It doesn't really matter. Okay, so I think this is enough for the introduction to the matrix algebra. In the next video, we're going to start tackling matrix multiplication. Thank you for your attention.